This molecule is 1-methylcyclohexane. And you can see we have a methyl group on one of the carbons in the ring. And in this case, in the flat ring, we see it going up from the ring. And so if we put this into a chair conformation, where we pucker one up, pucker one down, and get the chair conformation, we can see that the 3 axial hydrogens are here, and the 3 axial hydrogens are here on the bottom. And so, in fact, our methyl group is in the equatorial position. So it's going out from the ring. And here's the methyl group right here. Maybe hard to see. Okay, now if we do a ring flip, so the one that puckered up puckers down, and the one that puckered down puckered up. So if we do a ring flip, you can see that our methyl group has moved into the axial position right here. And so you can actually, as you turn that methyl group around, you can see that it sterically clashes with the hydrogen on the carbon 2 away from it. So this is called 1,3 diaxial strain. And it's a steric interaction because they're physically getting in the way of each other. And so big groups, like methyl groups, are going to be more stable in the equatorial position. There's just more room for it in the equatorial position. Okay, they're all going, it's going out and away from the ring, and so that is more stable. And so this PowerPoint slide shows you exactly the same thing. We can have that big group in the axial position or in the equatorial position, and those are differing just by a ring flip. And the more stable structure is always when the big group is equatorial. There's just more room. And if you were to draw a Newman projection of that ring, here's our front carbon, and then our back carbon and our back carbon. And so if you look at the chair conformation in that Newman projection, we have the 2 carbons, the 2 front carbons here that I'm holding, and then you put the back carbons behind them. So there's where my thumb is. And now we have this group here going down in the front, this going down in the front, just like it is in the diagram. And then our methyl group is going down off in this direction. So here's our 2 front carbons and our 2 back carbons. And then this methyl group is going down to the side. So if we do a ring flip, we see that the front carbons are here, the back carbons are here, and then that group goes up. And if we look at the model of that, we can see it here, where now that methyl group is axial. And here's your Newman projection with your front carbons and your back carbons, and the methyl group going down, and then that other group going up. And so this is a ring flip right here. So we have the methyl group or the substituent in the equatorial, and with a ring flip, it goes axial. And we can represent those either using Newman projections or regular line bond structures. So I told you the big groups like to be equatorial. Turns out 95% of the molecule has the methyl group in the equatorial versus 5%. And that's an equilibrium. So the conformation is going back and forth between these 2 conformations with 95% remaining in the equatorial position. And so this is what I just described. We have this 1,3 diaxial strain where the methyl group is physically hitting the hydrogens next door. It's a very similar interaction that we had when we had this gauche interaction, whereas in the equatorial, there's a lot more room out on the side. So equatorial is definitely more stable. And so this table just kind of walks you through the different functional groups. We can have chlorine, an OH, a methyl, an ethyl, an isopropyl, a tert-butyl. And the more larger you get in your substituent, the more strain we have for the diaxial interactions, and the more we get in the equatorial conformation. If we have a disubstituted cyclohexane, then we have to talk about whether they're up on the ring or down on the ring. Okay, so if we have a disubstituted cyclohexane, things get a little bit more complicated. So let's take a look. In this situation right here, we have a chlorine, which is above the ring, and a methyl group, which is below the ring. So if I make that molecule, it looks like this. Here's our cyclohexane, and here we have a chlorine that's yellow on this carbon going up, and a methyl, again, I'm just making it blue so you can see it on this next carbon, and that's going down. Make the chair conformation, so we'll pucker one up and one down, and we end up with the chlorine going up and the methyl group going down on the carbon right next to it. So they're both axial in that situation. And if I do a ring flip, then they both become equatorial. And so one thing I want to describe about this molecule right here is that these two groups, these two functional groups that are on the cyclohexane are trans to each other. So if they are on the same side of the ring, they're going to be cis to each other. And if they're on the opposite side of the ring, they will be trans. And so this compound right here, we would name 1, 2 trans, because they're on the opposite side of the ring. So 1, 2 trans. And remember, when 1, 2 trans gets folded into the chair conformation, they are either both equatorial or both axial. Okay, now looking at a different molecule where we have these two functional groups off of carbon 1, 2, 3, and we have trans 1, 3. Again, we could make this would be cis 1, 3. See, they're carbon 1, 2, 3, and they're on the same side. They're both going up, so cis 1, 3. And so this is a different molecule. When I have to break bonds, then that's a different molecule. If I can just rotate the bonds and change the conformation and do the ring flip, that's not breaking and making a bond. So that can be the same compound. So if I look at this one again, where we have 1, 3, carbon 1 and 3, trans. So I have 1, 3 trans, and I fold that into a chair, you will see that 1 is in the equatorial position and 1 is in the axial position. So the yellow right now is in the equatorial, but the blue is in the axial. So 1, 3 trans, 1 axial, 1 equatorial. Okay, so in a few minutes, I'll show you a little trick about that. Okay, so now if you're given this compound, for example, we have an ethyl group that's coming at us and a methyl group going away from us. This would be 1, 3 trans. And if we were going to name the entire compound, we'd call it cyclohexane. And we have a substituent that's an ethyl group and a substituent that's a methyl group. And so that would be 1 ethyl, 3 methyl cyclohexane. But we have to indicate the stereochemistry in the front. If you remember back to that nomenclature chapter, we have this thing called stereochemistry in the front of the name. And because these two functional groups are trans to each other, we are going to add the word trans to the beginning of our name. So that complete name is going to be trans 1 ethyl 3 methyl cyclohexane. And there's 2 ways that you can represent this molecule in a 3-dimensional format. One is where the ring is in the plane of the paper or the screen, and the groups either are coming at you or going away. The other way that we can do that is to draw the ring coming out of the paper or the screen or the board. So we're going to put dimensionality into the ring, and then we are going to say that the groups either go above the ring or below the ring. And so this could be our ethyl group and this could be our methyl group. Okay, so now here comes the hard part. Very often the next step in this process is to convert this type of ring or this type of ring into a chair conformation. So let me show you how I do this. I draw this little flat ring always as my little cheat sheet. And remember from the model kit that we learned in the last video, if this hydrogen right here is an axial hydrogen, remember the red and white, then the one next to it was equatorial and the next one is axial and right around. So I hope you remember that pattern. And then obviously the ones going down are the opposite. And so this is what it would look like. And so now if we have a compound that has an ethyl group going up and on carbon number 3, we have a methyl group going down, then we would take a look at carbon number 1 right here, and up is axial, and then carbon number 3 down is equatorial. And so we know that the carbon 1 now is going to be axial and carbon 3 is going to be equatorial. Carbon 1 is the ethyl group right here and carbon 3 is the methyl group right here. That's exactly what we do. We convert that to our chair conformation. We draw our chair, and on carbon number 1, and you can pick any carbon to be number 1, carbon number 1, we have an axial ethyl group. And then on carbon number 3, and again, you can go either direction, you need an equatorial methyl group. And so that would be the chair. And if we draw the ring flip, we just do this pattern backwards where we go off this side. And so now we have our ring flip. And so if this is carbon number 1 right there, then this is carbon 1, and it went from axial here to equatorial here. And so there's that. Carbon number 3 was equatorial, and now it's axial, and so that's going to look like that. And so here is the 2 ring conformations of this flat ring that was drawn above. If we had to decide which was more stable, we would say that the bigger ethyl group needs to be an equatorial. The equilibrium would actually probably be more like that, where this one is favored because the big group is in the equatorial. And so if my drawings were a little bit messy, here's what happens. The question would be draw both chair conformations for the following molecule. And so there's the molecule that we're given. And I quickly see that this is 1,3-trans. So I draw my quick little cheat sheet here, and I see that if 1,3-trans is going to be axial equatorial. And so I know that when I draw my chair, one is going to be axial, one is going to be equatorial. And when I do a ring flip, they switch. So it doesn't really matter which one we do first. And so here is the formal answer to that question. 1,3-trans is 1 axial, 1 equatorial. And then we do the ring flip. And I showed you here that that's going to be a little bit more favored because the bigger group is an equatorial. So here's the naming that we talked about earlier. Cis would be the same side and trans would be the opposite side. And so we're going to describe the orientation around the cyclohexane ring. If they're on the same side, they're going to be cis, and if they're on the opposite sides, they're going to be trans. These 2 compounds are different. They are called stereoisomers, and that is why it falls under the stereochemistry part of the naming. Up here, we have the example where we have 1, 2, cis, and if you go back to my cheat compound, 1, 2, cis, one's axial, one's equatorial. And sure enough, one's axial, one's equatorial. And in this case, they're going to be equal energies because one is a methyl group and the other is a methyl group. So they're the same. If we have 1, 2 trans, then if we go back over to my cheat molecule, we have 1 equatorial and the other one's equatorial as well. And so we end up with diaxial or diequatorial. And of course, the diequatorial is much more stable. So that equilibrium arrow might look more like that. So the one with equatorial is more stable. And here's a slide I made just to help you kind of comprehend this whole thing and put it all together. So if you are unsure if this is the best way for you to memorize that, using this little molecule as a cheat sheet, here's another way that you can do it. Every time you have a 1, 2 cis, it's going to be 1 axial, 1 equatorial. Anytime you have 1, 2 trans, it's going to be both axial or both equatorial. Anytime you have 1, 3 cis, you're going to have both axial or both equatorial. And if you have 1, 3 trans, you're going to have 1 axial and 1 equatorial. And if you have 1, 4 cis, it's the same as the 1, 2 cis. And 1, 4 trans is the same as the 1, 2 trans. This is going to be 1 axial, 1 equatorial, and 2 axial or 2 equatorial. And 1, 5 is actually the same as 1, 3, okay? And that's going to be 2 axial or 2 equatorial, and 1 axial, 1 equatorial. So if you don't like this, you can use this. And I can remember when I took this exam, I walked into my test, and at the top of the page, I wrote 1, 2 cis equals 1 axial, 1 equatorial, 1, 2 trans equals 2 axial or 2 equatorial. And from there, I could figure anything out, because the even numbers are all going to be like this, and then the odd numbers are going to be the opposite. So I hope that helps. But the good news is you can bring your model kit to the exam. So if you see 1, 3 trans and you're unsure if that's going to be axial, equatorial, whatever, you can always make the model and then make the chair And then you see 1,3 trans is in fact 1 equatorial, 1 axial. And you're welcome to walk into the exam with cyclohexane already made. Okay, this is definitely a little bit challenging. Definitely do some practice problems with SI and in the textbook. And I wish you the best of luck. Thanks.